In the last class, we started embarking on the analysis of the proton spectra consisting of heteronuclear couplings, both abundant spins and dilute spins. Especially when we have abundant spins like phosphorus and fluorine, spectrum becomes a bit complex because splitting is directly reflected on the spectrum, multiplicity pattern would be there, and you have to analyze this to extract the coupling information. And I took several examples and showed how we can get heteronuclear coupling when single heteronuclear is present or both or two extranuclear present or more than that. And also what will happen is sometimes the heteronuclear need not be 100% abundant, there could be dilute spins, less abundant spins. For example, carbon 13, nitrogen 15, silicon, etc. Their abundance is very small, and these only interestingly such type of isotopomers are NMR active, they can give rise to coupling with the abundant spin to which it is coupled to. And I took the example of tetramethylsilane, where coupling of silicon with proton I saw, and I showed how we can measure that. At the same time, it has also got carbon. Carbon 13 and silicon both will couple to proton and give rise to satellite peaks on either side. Similarly, to CHCl3, there is only one carbon, but single proton comes because of 99% of the molecule containing carbon 12, which does not split. It gives a single peak, strong, huge, intense peak is there. Then carbon 13 is 1% of the molecule, which couples to proton, splits this into a doublet. Because of the 1% abundance, intensity is 1%. Further, due to splitting, it becomes 0.5%, and they are called satellites. So, in one molecule there can be satellite corresponding to one less abundant spin. You can also get peaks corresponding to 2 or 3 less abundant spins, for which I took the example of tetramethylsilane. So, and I also took the example of SiHCl3, where in the proton spectrum SiH coupling of nearly 340 or 350 hertz we could easily see, and they are very weak in intensity. And the intensity of the satellite depends upon the abundance of the dilute spin. It can be, for example, carbon 13 1%, nitrogen 0.37%, silicon may be 4%, 7%, selenium may be 4 or 7%, like that it can vary. Okay. So, with this we will now go further and take few more examples, and I would like to finish the analysis of the proton spectrum today, so that we can go to heteronuclei tomorrow at least. Another example of this thing, this we discussed, selenium satellites. I want to show this proton spectrum of paraxylene. It is a very simple molecule, and all 4 proton of aromatic protons are equivalent here, and 2 CH3 groups are equivalent. CH3 group is going to give you a strong peak, but on either side of it you see 2 small peaks, they are satellites. Of course, here also you can see, if you carefully see, there are peaks which is not shown, but here very clearly visible. Okay. We can see that and measure the separation, you can get SiH coupling. This is from the ring proton, this is from CH3 proton, and carbon 13 satellites are there. So, okay, carbon 13 satellites we saw, silicon satellites we saw, selenium satellites we saw. Look at the mercury. Mercury is another thing, very low abundant. And if I look at the mercury spectrum of dimethyl mercury, mercury 199 if we took, mercury 201 is there, but 199 mercury is one which is usually practiced. And look at it, these mercury satellites, mercury coupling appear as satellites, and it is huge coupling of the order of 100 hertz. See, in the heteronuclear couplings can be very large values. Homonuclear coupling we saw, of the order of proton coupling, maximum was 284 for proton, 2 hydrogens, hydrogen atom when 2 protons are 1 bond separated. Whereas in the heteronuclei, the coupling can be enormous, sometimes can be of the order of several thousand hertz. Simple example I am showing you here. In the case of mercury is also 100 hertz. These are mercury 199 satellites coupled to proton. This platinum coupling. Platinum is, you look at the 1H NMR spectrum of platinum, a small complex. We are looking at the proton, but especially I am concentrating on this proton H2 of the ring. Of course, we are not worried about it. Since we are worried about only the satellite in this part, I am not looking at the other spectrum corresponding to other protons. We will worry only about this and see how we can get the coupling. This proton, of course in the phenyl group I told you, it can experience coupling with orthoproton with this one, which is quite large, and then with this one. But when there is a heteroatom, I told you ortho coupling will be very small. Okay, 3GHH coupling about 6 Hertz, 4GHH coupling is there about 2 Hertz, and this can also couple to phosphorus here. Phosphorus is there. This is separated by 1, 2, 3, 4 bonds. It can couple to phosphorus. That is very large. 4 bond phosphorus coupling, and it can also couple to platinum 1, 2, 3 bonds away, and that is quite large. So this one proton can simultaneously experience coupling with abundant spin and also dilute spin. Abundant spin is phosphorus and dilute spin is platinum, and in addition to that it has coupling with other 2 protons. So it is a very complex pattern, and interestingly this proton spectrum has been recorded at 3 different resonating frequencies. You can see at 90 megahertz at low frequency, you can see these are the peaks which are coming here. Okay, these are the peaks which are coming. What are these peaks? As you go ahead, you see at higher frequency these peaks are getting broadened out. You are not seeing, and these things, one proton can experience coupling with 2, 3 and 4. It will be very complex. 2 to the power of 4, it should be 16 lengths could be present here. The multicity pattern is because all the couplings are different. Doublet of it will be DD will be there 4 Ds. So it should be 16 peaks are there, and if you carefully see, identical pattern is in either side. That is because 8 peaks are here, the remaining should be with the platinum. They come as a satellite. Okay, and that is seen here, platinum proton coupling for this one, and other couplings are seen here because they are abundant. Platinum coupling is appearing as a satellite here. Identical pattern you see, exactly like the pattern of the main peak. Okay, that is what you see. And increasing the resonating frequency, interesting thing happen, this will reduce. This is to do with what is called chemical shift anisotropy, relaxation due to chemical shift anisotropy. This becomes more and more at higher and higher frequency. So we will worry about it when we come to relaxation part, when I discuss relaxation. But right now you remember, we have coupling of this proton to all the 3 abundant spin plus 1 less abundant spin which come as a satellite. This is called platinum proton satellites, platinum coupling. Okay. So far we had understood one thing. From the satellite analysis we got the satellite and less abundant and high abundant spin coupling. Okay, like proton carbon, proton nitrogen, proton selenium couplings we got. Can we get the proton proton coupling in the satellite spectrum? Is it possible to get it? Why not? We will see that example. Take the example of 1,1 tetrabromoether. Is a molecule, is a simple molecule. These 2 protons, if you carefully see, they are chemically equivalent. How many peaks it will give? It will give only a single peak. When there is a single peak, how do you get the HH coupling? You cannot get. At least there must be a doublet to measure the separation and to get the J coupling. So chemically equivalent spins, couplings are not reflected. Even this spectrum splitting pattern is not seen, and couplings though present are not reflected in the spectrum. Not that coupling is absent. Though it gives a single peak, there exists a coupling, transcoupling between these 2 protons. But unfortunately, that coupling is not reflected in the spectrum. As a consequence appears, we get a single peak. But I tell you, there exists a coupling, how do you measure it? This is what we do. We break the symmetry of the molecule. Remember, when I was explaining to you about Popper nomenclature, these 2 are chemically equivalent, we call it as a A2 spin system. But this A2 spin system, what I will do is, this is A2 when I look for only carbon 12. But I am going to a situation like this. In this sense, instead of carbon 12, I look for carbon 13, 1% of the molecule. Then what will happen? If I say instead of carbon 12 there is a carbon 13 here, carbon 13, this is a 1 bond coupling, this is a 2 bond coupling, they are different. That means symmetry is broken. You have broken the symmetry of the molecule. That means the A2 spin system, which is the nomenclature for this molecule, purple nomenclature, now we call it as AA prime X. What do you mean by AA prime X? I told you while explaining purple nomenclature, these two are chemically equivalent, but there exists a coupling between them which is not reflected. Now you can see the coupling. When in the A2, you will not see the coupling, even though it is present. But in AA prime, you can even extract the coupling information. And for that, you broke the symmetry by bringing in carbon 13 in its natural abundance. Of course, you can label it if you want, but we took only natural abundance. In which case, what happens? Since it is AA prime X, I am going to enhance it. I see the satellite here. So, this satellite will couple to the 1 bond coupling is here. This is a 1 bond coupling, 1JCH. But remember, this satellite is not a singlet here. Each of them is a doublet. Why the doublet is coming? If I consider this proton, this is a 1 bond coupling, plus because symmetry is broken, this is also coupled to this, that is getting reflected in the satellite spectrum. So, this doublet separation correspond to JHH. This correspond to JHH, this separation correspond to 1JCH. So, you can get the homonuclear coupling, which is not possible to get in the proton spectrum because of chemical equivalence. You can get from the satellite analysis, because you are breaking the symmetry of the molecule by bringing in less abundant spin. You are not doing anything for the molecule, just you look at the molecule with isotope with carbon 13 present, that is all. Then you are breaking the symmetry and couplings of proton-proton is seen here. This is what it is. Same thing you can do here. This is Sa2H6 molecule. Now we have silicon, which is 4.7% abundant, plus we also have 1 bond and 2 bond coupling. This silicon has 1 bond coupling here and also has 2 bond coupling here. There are 2 types of coupling you can think of. If you take the proton NMR of it, this correspond to one of the things. Silicon has several satellites, several isotopes, several isotopes. But we are considering only for Sa29, which is coupled. All other things other than 29 will be here, which gives us a single peak. When there is Si29 present, symmetry is broken, then you will get coupling of this with this, coupling of this with this. That is also possible. So, now we are going to get the coupling like this. This is 1 bond SiH coupling. Okay. 1 bond SiH coupling, but at the same time you are going to get here 3 bond HH coupling. Each of this proton, because symmetry is broken, this will become a quartet. You see, this is a 3G HH coupling you are going to see, a 1 bond SiH coupling. But carefully if you see, this can also have a 2 bond SiH coupling, which is not seen here because they are hidden within the strong peak. Under the strong peak, they are hidden. As a consequence, you are not seeing it. So, you can see the satellite spectrum. From the satellite, you can also get the proton-proton couplings. This is classic example of another molecule, where again these two are chemically equivalent. You get a single peak here. This corresponds to the situation where both the carbons are carbon 12. And of course, these are all some of the satellites and sidebands, and you do not worry about it. What is happening is, I am considering a situation like this, where one of the carbon is, instead of carbon 12, I consider it as carbon 13. Again, you have broken the symmetry. Since you have broken the symmetry, now you are having a strong peak here. On either side of the strong peak, you have satellite peaks here due to 1 bond proton carbon coupling, and each one of the satellite is a doublet because of proton-proton coupling. So, from the satellite analysis of this molecule also, you can get the HH coupling. Okay. These are all some of the examples where you can get it like this. Okay. You can continue like this with large number of examples. In this case, this is a spectrum of 2-propanol, where 2 CH3s are present here. They are all split because of CH proton here, and it is a doublet. If you expand it, and each of them is going to be a doublet, it's a satellite pattern. Each lane of the satellite is a doublet, and this separation from this to this gives you CH coupling, whereas this separation gives you HH coupling. So like that you can get lot of these things, and of course there is no point in going further. We are going through this. You can have large number of such examples, but I want to show you one example like this, where a molecule like this, if there is symmetry is not broken, both are identical, these protons are identical, these are identical. Whereas when I take the NMR spectrum of it, you see this one proton etc. easily. But I have expanded two peaks here. These two peaks correspond to these protons. Okay. And not those two protons. One is of course one is this proton, other is this proton, because there is a symmetry. If you carefully see, each of them is a doublet. Why each of them is a doublet? There is a HH coupling, geminal coupling is there. At the same time, each of these protons can experience coupling with silicon. It can have 3 bond silicon, this proton coupling, silicon to this proton coupling. Both are present. Both are 3 bond coupling. See, this is what it is. One proton and one proton, both are here. This proton is coming here and this proton is coming here. You see, you can find out from this. Sorry, okay. This proton is because of this, and this proton is because of this. Okay. But on either side of this thing, you get satellite peak because of selenium coupling, and each of the satellite is a doublet which gives rise to HH coupling. Not only you can get here, you can also get from the satellites here. Okay. So far we discussed a lot about varieties of things. But remember, what did we discuss? We discussed coupling between proton, selenium, silicon, phosphorus, fluorine, etc. Most of them are, or all of them I would say, are spin-off nuclei. Proton is spin-off, all are spin-off nuclei. So coupling of spin-off to, of course I took the example of boron 10 and boron 3/2. Okay, apart from that, most of them I took considered as a interaction with the spin-off nuclei. But there can be coupling between spin-half and spin-1 nuclei, or more than that. We will see now. Take the example of proton spectrum of NH4Cl. NH4Cl, interestingly, nitrogen 14 is highly abundant, almost 99.6, and 0.37 is the abundance of nitrogen 15. And N14 is spin 1, N15 is spin half. So N14, when it is coupled to proton, it will give 3 lines of equal intensity, 1:1:1, because there are 3 possible spin states, +1, -1, 0 and +1, 3 possible spin states. So it gives 3 line pattern. Whereas nitrogen 15 spin half, it has only 2 possible spin states, alpha and beta. As a consequence, it will give 2 lines, only doublet. But look at the intensity. This is 0.37 abundance of nitrogen 15. Further it is split into 2. Very, very weak intensity, you will not see that. So nitrogen 15 gives a weak doublet, it is a satellite. Whereas proton coupled to N14 is a abundant spin, we give 3 lanes of equal intensity. Where else you can get this example? Look for carbon CdCl3. When I come to carbon NMR, I will show you. Carbon coupled to deuterium, deuterium is spin 1, carbon is spin half. We get 3 lanes of equal intensity there also. So when the spin off nuclei is coupled to spin 1 nuclei, each line is going to be split into 3 lines of equal intensity, whereas spin half nuclei gives a doublet like this. Okay, this is an example of nuclei spin greater than half. This is a germanium 73, spin is 9/2, abundance is about 7.7%, and I am looking at the proton NMR. How many peaks I expect for this? Of course, this is germanium 73 will give rise to coupling like this. The one which is high intense is correspond to other isotopomer which does not couple to proton. Whereas germanium 73 is spin 9/2. So how many peaks it will give? Put it into this equation, you are going to get 10 peaks. What is the intensity? almost 7.76, close to 8% compared to the strong peak. You count, there will be 10 peaks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this intensity ratio is almost 7.7 or 8% with respect to the strong peak. This is a coupling of germanium with proton whose spin is 9/2. Germanium spin is 9/2. With this, I am going to introduce another term called coupling between magnetically equivalent protons. That is something interesting. What is that? Consider the proton-proton coupling in hydrogen molecule. How many peaks it will give? There is a symmetry. It will give only one peak. Take the proton NMR spectrum of hydrogen molecule, you will get only one peak. But remember, I told you JHH in hydrogen molecule is about 284 hertz. In one of the classes I said it is 284 hertz. Huge coupling is there, one bond coupling between two protons. How did we get this? How did I know there is a coupling between them? Because it proton NMR gives a single peak. Then what is the way I can measure the coupling? How did I know that? There is a way. What you have to do is, in such cases, we do what is called isotopic substitution. In the sense, molecule should remain same. You can't have another substitution. Then molecule will be entirely different. I want to retain the same molecule. Characters should be remaining same, but I must extract the coupling. Easiest thing is simply remove one of the protons by deuterium. Two isotopic labeling. Now what is happening? Symmetry is not there. You have broken the symmetry. Like we said, when carbon 13 is there in CaCl3 symmetry, in some of the molecules I showed you, when I took carbon 13, symmetry was broken, A2 became AA prime X spin system, Like that, here symmetry is broken. Then this deuterium can couple to proton. You should now be able to understand what is the pattern we are going to get for this molecule. If I look at deuterium which couples to proton spin half, it will be a doublet. If I look for proton, it is coupled to deuterium which is spin 1, so it will be 3 lines of equal intensity. I told you NH4 an example, nitrogen 14 spin is 1, it gives 3 lanes of equal intensity. Similarly, deuterium is going to give 3 lanes of equal intensity here because HD coupling. So, okay, I get a spectrum like this. Then what are you going to do here? If I measure the separation, what do you get? You measure this, you get JHD. Fine, I got JHD, but I still not got JHH. My idea is to get JHH. JHH is the one which is not getting reflected in the spectrum. JHD, if I get, what is the use? But remember, this is a fantastic, very good formula. If I know J coupling between proton and deuterium, I can get the coupling JHH by using the ratio of the gyromagnetic ratios. For example, proton deuterium gyromagnetic ratio is 6 times 6.488, 6.5 times you take approximately. So, if I know this ratio, and this is the equation which relates the coupling between HD and HH. If I know J between proton and deuterium, I can calculate this by taking the ratio of this. Remember, JHH or JDH is equal to gamma H or gamma D, and this ratio is known 6.488, and I know this one. Then how do you get it? So, JHH is going to be 6.488 into JDH. 6.488 JDH I can measure from this separation, which is 45.54 hertz. So, multiply this by 6.488, you got this 276. This is what the HH coupling. In a molecule like hydrogen molecule, where there is a perfect symmetry, you will not get the HH coupling, but by isotopic substitution you get JHD. When I know JHD, I know the ratio of the gammas between proton and deuterium. Simply multiply JHD by the ratio of proton gamma Y over deuterium gamma, you get HH coupling. Very simple. This is how you can get the J coupling between magnetically equivalent spins. Take for example benzene. All 4 protons, all 6 protons are equivalent. It gives a single peak. Then how did I say there is ortho coupling of 8 Hertz, meta coupling is of 1.5 Hertz and para of 0.5 Hertz? How did I say that? One way is you can do isotopic substitution. Otherwise, break the symmetry by looking at carbon 13, which you already did that earlier. So when you break the symmetry looking at carbon 13 present at one of the sites, then it is going to be AA prime, B prime, C, DX, some particular spin system. Then analyze that carbon 13 satellite spectrum, you get, or carbon 13 spectrum directly, you will get JH, carbon and CH coupling and HH coupling, everything you will get. Of course, carbon if you analyze, you do not get HH coupling, but you analyze proton spectrum with satellites, you get HH couplings also. That is how we get couplings in the magnetically equivalent spins. Like take for example CA3CN. CA3CN, if you determine, how do I determine the J coupling? CA3CN is astronitrile, all the 3 protons are magnetically equivalent, you get a single peak like this. This corresponds to a single peak of CA3CN. But what do I do? Just now I told you, we can do isotopic substitution. I will knock off one of the proton and put a deuterium. Then I will look for CH2 proton. Because of deuterium, it is going to be 3 lines of equal intensity. Deuterium is spin 1. Now measure the separation. It gives you JHD. Use the JHD. Use the ratio of the gamma proton or gamma of deuterium 6.488, whatever I gave you. Multiply by this, you get the HH coupling. Alternately, you can also do other one. Instead of 1 proton, you can replace 2 protons by deuterium, then it will become CH_D2CN. Then you get 5 line pattern. Because 2 deuteriums are there which is coupled, you are going to get 5 line. Remember when I explained CH2D2 molecule, I showed you we get 5 lines of intensity 1, 2, 3 to 1, if you remember that, for the 2 deuterium coupled to proton. Similarly here we got 5 lines for the proton CH_D2CN, and you measure the separation of this exactly this molecule, you will directly get the JHH. From the HD you can calculate JHH. You may ask me a question, I replace all the protons by deuterium. Then you can't do it because there is no proton. Then of course you can do it by going to carbon 13, but you get carbon deuterium coupling, carbon proton coupling, but HH coupling you do not get. So that means you can't have all the protons replaced by deuterium. You understand? So we remove one of the proton by deuterium, replaced by deuterium, or 2 of them, and get the multiplicity pattern, analyze it, and you get the HD coupling and calculate HH coupling. So in this case, for example, JHD 2.58 was the value. After multiplying with JHH, we will get 16.8. So astronitrile, though gives a single peak in NMR, in reality coupling between or among any of the 2 protons in CA3 group is 16.8 Hertz. There is a way we could measure the coupling. Look at the CH2Cl2 molecule. How many peaks it gives? CH2 proton NMR gives a singlet. What I do is I make it CH_DCl2, replace one of the proton by deuterium. I am giving another example just to make you more comfortable. So this is third example I am giving how to get the coupling among the magnetically equivalent spins. Now proton couples with deuterium and gives 3 lines of equal intensity. We got it, measure it. Use my formula JHH over JHD, which is equal to gamma H over gamma D, whose value is 6.488, whatever it is I told you already. Calculate it. Gamma H over gamma D 6.5 or whatever that value, and you get the coupling. So this is the real spectrum of CH2Cl2. The 1H NMR spectrum of CH_DCl2. This is CH2Cl2 spectrum, which is a singlet. This is replacing one of the proton by deuterium. You got 3 lines of equal intensity. Realistic spectrum. And JHD was measured to be 1.104 here. And then using this ratio, we calculated JHH as 7.192. Okay, this is what it is. So in the magnetically equivalent spins, we know how to calculate the how to determine their couplings, even though the coupling is not reflected in the spectrum. All you have to do is the isotopic substitution. Whereas in molecules like benzene and others, you have to break the symmetry by taking into account carbon 13. Then you will get HH coupling. That is how we could get all the information. And with this, I want to tell you one more small thing very quickly. Wherever there is an opportunity, if the spectrum is complex, we can remove the complexity by doing what is called decoupling. I will tell you more about decoupling later. Quickly I will show you one or two examples. In this molecule, look at this proton 6. Look at this fluorine. They are very broad here. Proton 6, you look at it, very broad. Do not worry about the analysis part. Whereas what I am going to do is I will do nitrogen 14 decoupling. What do you mean by nitrogen 14 decoupling? I will break the coupling of nitrogen 14 to proton. How I do? I will tell you when I explain to you the decoupling. So simply we have to saturate that nitrogen 14 so that this proton does not see nitrogen 14 in any of the 3 states, -1, 0 or +1. Then you see the broadening disappears and we get sharp peaks. Very easy. Or you can do one thing. I want to get the spectrum of proton by decoupling fluorine. That is also possible. Then you break the proton fluorine coupling and you get only HH couplings here. There is no FH coupling. This is a real spectrum where HH, FH coupling both are present. But here FH coupling is removed. From this spectrum you get only HH couplings. Understand? If you analyze the spectrum, you have to get HH coupling and HF coupling both. But here you get only HH coupling. Then you may ask me a question, can I remove HH coupling and get only FF coupling? That is also possible. There is a way of removing proton-proton couplings. It is not easy. When we have to discuss about the pure shift, I will have to tell you that. There are several experiments called pure shift experiment where broadband we can remove all the protons coupled among themselves. Here no protons are coupled. All we can remove by using a technique called Psyche. Then HH are removed. What is that left here then? Only FH coupling. See the way. When the spectrum is complex, there are ways of simplifying it. When it is too broad, we made it sharp by decoupling N14. When the spectrum is too complex, in the previous example like this, we made it simple by by removing fluorine coupling, and here even simpler by removing proton-proton coupling, we get FH coupling. Like that we can get a complete information about all the coupling can be obtained like this. So like this, of course, this is the example where it is too complex for a molecule with phosphorus. This is a CH3 group with a CH2 group. See, it is very complex. This is coupled to phosphorus and CH3 group is a doublet because a long range coupling. Whereas I go to decoupled, this is disappeared. This is also fairly simplified. So what I am trying to say is there are a number of ways you can analyze their proton NMR spectrum. In summary, we took lot of examples where homonuclear coupling, heteronuclear coupling of abundant spins, heteronuclear coupling of many abundant spins present in the molecule, heteronuclear coupling of less abundant spins, less abundant many spins present in the molecule. And when it is too complex, how I can simplify it by taking in by breaking the coupling between proton to other abundant spin, or even you can do coupling by breaking the coupling with a less abundant spin like carbon 13. Lot of things are there. When the spectrum is too broad at times, because of the nitrogen 14 or oxygen, we can do even that decoupling also. Nitrogen 14 decoupling to sharpen the seek. So all these tricks we can adapt, and I give a number of examples to see how we can analyze the spectrum and get the information, make the assignment of chemical shifts and extract the coupling information, which helps in getting the structure of the molecule, conformation of the molecule later. So we have extensively discussed about proton for a long time. In the next class, I will go for carbon 13 and lot of things we have to discuss about carbon 13 and also about other heteronuclei. Then subsequently you move to 2D NMR, where there are too many things to discuss in 2D NMR also. So I will stop here and we will continue with the carbon 13 NMR in the next class. Thank you very much.